Assalamu alaikum students. Today's topic is going to be about speed of sound. Before moving on towards our topic, let us discuss about wave because sound are waves. So what is wave? Basically, it is the disturbance in a medium by which energy can be transferred from one place to another like this. This is a wave. Now, how many types of waves are there? There are two types of waves. First of all, there is electromagnetic. Electromagnetic waves. These are those waves which do not do not require do not require a medium to travel from one place to another. Whereas mechanical waves are the second type of wave which requires a medium to travel from one place to another. Now, let us understand with the help of example. The example of electromagnetic wave is light. Now, as you can see, light from the sun travels through vacuum to the earth, whereas the mechanical wave, we have example of sound, and sound requires a medium to travel from one place to another. And that is why we can hear sound because air, there is air or medium is present. Now, mechanical waves are further divided into two parts. One is longitudinal wave, and the second one is transversal wave. Now, what are transversal wave first? Now, if we consider an example of a slinky and we move it up and down, so we can see that the particles of this slinky is moving up, whereas the wave motion is moving in the forward direction. So they are making an angle of 90 degree or perpendicular to each other. So these type of wave in which the particles and the movement of wave motion are perpendicular to each other, such type of wave is known as transversal wave, where the upper part is known as crest and the lower part of this wave is known as trough. Similarly, in this longitudinal wave, we are now not moving it upward or downward like in this case, in the case of transversal, we are moving the same slinky but forward and backwards. So it will compress the spring or you can slinky at certain places and there will be a rarefaction or you can say further part over here and again there's a compression over here, so there will be two parts of this wave, but in this case we can see the particles of the spring are moving in the same direction as the wave motion. So in this case, if the particles and the wave motion are moving parallel like shown over here, if they are moving parallel to each other, then it is known as longitudinal wave. The compressed part are known as compressional region, whereas the rarefaction, the longer part, is known as rarefaction. Now, as we are discussing the sound, so now we know that it is a wave. If we summarize it, that this is a wave which is mechanical wave, and it is a longitudinal wave because it requires a medium to travel and the particles basically move perpendicular to the wave motion. Now let's calculate what is speed of sound. Now first of all, the definition: the distance traveled by sound wave per unit time is called speed of sound wave. Sound waves are compressional wave in nature. The speed of mechanical medium, because it requires a medium to travel from one place to another, a medium depends upon two characteristics in a medium that are: number one, density, how much dense a medium is. If the medium is much more denser, the sound will travel much more faster. If the medium is less denser, the sound will travel less faster. And the second thing is elasticity of the medium. That means when the deforming force is removed from that medium, it basically returns back to its original position, or we can then say in simple words, the ratio between stress and strain. The expression for the speed of sound in any medium was given by Newton and can be written as speed is equal to under root elasticity modulus of the medium divided by the density of the medium. We can simply write it down in symbolic form as V is equal to under root E divided by rho. Let's call this equation A. We have to remember this equation A because it has to be used again and again. This is equation A. V is equal to under root E divided by rho, where E is the elastic modulus and rho is the density. Now let's see how Newton solved this equation. Newton assumed that the sound travels through air and other gases under isothermal condition. Now, what is isothermal condition? The isothermal condition are those conditions in which temperature remains constant. That means it doesn't change throughout the experiment. Those are isothermal conditions, which means that when sound wave travel in the air, there is no change in temperature. Under such condition, the modulus of velocity is equal to pressure of the gas, and which can be proven as follows: that let's assume that V be the volume of the air pressure at P, and if we increase the pressure from, let's say, P to delta P, let's say P to, let's say, P plus delta P, and volume will decrease from V to delta V, or we can say V to minus delta V, keeping the temperature constant by applying Boyle's law. Now in this case, let's explain this whole concept very simply, that if we have a cube over here and it is a volume, as you can see over here, and if we apply pressure on all the sides of this cube, will the volume increase if we increase the pressure? Yes, the volume will decrease. So volume decreases. So as we are increasing, or we can say increase the pressure, we can see that the volume delta V has been decreased over here. And all of this is under the action of isothermal condition, in which we say that it is at constant temperature, which is basically Boyle's law. Boyle's law said that pressure and volume are inversely proportional to each other at constant temperature. Considering that into our minds, we have to understand this important point, that Newton assumed that all of this was happening at isothermal condition. Now, if we consider this equation of Boyle's law, that PV is equal to, if the change is there, if we increase the pressure, the volume will decrease. Now, if we multiply these values, what do we get? Now, let's see that PV is equal to, if we multiply this P with this V and then this P with this delta V, so what do we get? It will be PV minus P into delta V, and when we multiply this delta P with this V and then this delta P with this delta P, it will be plus delta P into V minus delta P into minus V. Now this is what we have gotten over here. Now if we look at this equation, this PV and this P will basically cancel out with each other, and if we take this negative sign to the other side, it will be, after this step, is written as minus P delta V plus delta PV minus delta P delta V, and if we take the negative sign to the other side, it will be P delta V is equal to plus delta P V minus delta P delta V. Now this is the next step. Let's check it out, that PV is equal to delta P minus delta P into delta V. Let's call this equation number 1. Now, as it is equation number one, but these values are very, very small. We already know the delta means a small change, but when two small values basically multiply, they become even smaller. If the increase in pressure is small, then the decrease in volume is also small. So we have to neglect delta P and delta V. So it will be equal to 0. Let's consider it to be 0. So what we are left with now? We are left with now delta P, del P into delta V is equal to delta P into V. This is equation number 2, which is very important. Now, if we rearrange this equation, let's say P delta V is equal to delta P V, which is equation number 2, and we write it like this: P is equal to delta P into V divided by delta V, and this V can be also written as P is equal to delta P divided by delta V divided by V. So this is the new form of the equation. We can rearrange it in mathematical procedure. Now, this is the form which we have gotten. P is equal to delta P into V divided by delta V, and we have taken the V down, delta V, so it can be written as delta P divided by delta V divided by delta V. Now, why we have done this? Because we can see that this thing, this pressure, delta pressure, can be represented as force per unit area, and this delta V, which is change in volume divided by its original volume. Now this formula looks similar to some formula which we have done before. This can be stress, because stress is also force per unit area, and change in volume divided by its original volume can be called strain. Now we have a new concept over here. The pressure is equal to stress over strain. So let us write it down. Pressure is equal to stress over strain, and we said that elasticity, elastic modulus is also the same thing, stress over volumetric strain. So we are now putting P is equal to E. This is the main concept. That is why we rearrange the V and delta V in the equation. Now, if we remember the formula in the first slide, that V is equal to under root E divided by rho, and if we replace this P with this E, what do we get? V is equal to under root P over rho. Now, the new equation will become, as we know that E is the elastic modulus or elasticity of isothermal process. So the speed of sound in air or gas is V is equal to under root P divided by rho. Now we have to write down the values of P. Now, as we know that P is equal to force per unit area, we know that force is basically the weight of that object under it, which is basically going through, and area will be written as it is. Now, from the definition of density, we know the density is equal to mass per unit volume. We can say mass will be equal to density into volume. Putting the value of m in this equation, what do we get? P is equal to, instead of m, we can write down rho Vg divided by A. And we can understand the definition of volume as well. Volume is equal to area into height. You can see over here, this is a cube, this is the area, and this is the height we can see over here. So if we multiply this whole volume, we will be figured out. Let me draw a nicer diagram over here so you can understand. This is the volume. We have understood this area, and this, let's say, is the height. So the total volume will be equal to area into height. Putting this value of V in this equation, what do we get? P is equal to rho, which is the density of that medium. V will be represented by AH, and G is the gravitational acceleration divided by A. So this A and this A cancels out. What we are left with? P is equal to rho m into G and H, and that is why we are now going to take P is equal to rho mgh, where m is representing the density of the medium. Now, where P is the pressure and rho is the density of the gas, the Newton's formula of the speed of sound in air can be now given as P is equal to rho m, which is the medium density of the medium into G into H. Now the new thing can be written as, or new equation can be written as V is equal to under root rho m, that means density of the medium into gravitational acceleration into height divided by density of the air. Putting in the values, and we have the values where rho m is the density of mercury as standard temperature pressure, and the density of the medium is 13.6 grams per centimeter cube. The value of G is taken to be in centimeters, 980 centimeter per second square, and the height is taken to be 76 centimeters. Now, and the density of air, rho, is taken to be 0.001293 grams per centimeter cube. Now, if we put in the values of all these experimental values in this equation, what do we get? We get V is equal to under root 13.6 into 980 multiplied by 76 divided by 0.001293. We get a velocity of 281 meter per second. But this is not the velocity which we had in our minds. If we remember that, how, let's do an experiment that this is a cliff and a person is standing over here, and basically he claps, and the distance between the cliff and the person is, let's say, 17 uh, meters. Let's say this is 70 meters. The clap basically goes on to the cliff, strikes back, which is known as echo, and comes back to the human ear in 0.1 second. This is the requirement. So time is also with us. So how much distance has the body or the sound actually traveled? 17 centimeters in this direction, 17 centimeters in this, not centimeters, sorry, 17 meters in one direction and 17 meters in the other direction. It will be total 34 meters. So we have the displacement over here, and we have the time over here. Distance is also given and the time is also given. Now we have to find the velocity. Velocity is equal to displacement over time. Displacement is taken to be 34, time is taken out to be 0.1. So approximate value of speed of sound is 340 meter per second. Now, this was the value of speed of sound approximately. But if we do much more precise experiments, the experiment value of speed of sound in gas is 332 meter per second. Thus, this is not our required answer. The theoretical value is 16% less than the experimental value. Now, what do we have to do? There's some mistake in this derivation. So, there was another scientist by the name of Laplace. Basically, he found out the correction in this derivation. So, a French mathematician, basically, by the name of Laplace, explained the discrepancy in theoretical and experimental values of speed of sound in gas. Laplace argued that the sound waves are longitudinal waves, which consist of compressional and rarefaction. That means we knew that the sound waves were basically compression. That means they are compressed at certain regions, we call them C, and they are rarefaction at certain regions, which are R, and they compress again, which is C. Now he says that the compression at the temperature of the rise, that means wherever there is compression, the pressure basically increases, and due to that reason, the temperature in that region also increases. And we can say that at compression, the temperature of the air rises due to the increase in pressure, and at the rarefaction, the cooling effect is produced. That means at rarefaction region, the temperature basically decreases. Again, it will be increase in the compression age region again. So the temperature of the gas does not remain constant. That was the mistake. Hence, Boyle's law is not applicable. That was the mistake which Newton did. Laplace basically also said that air is a very poor conductor of heat, and sound wave travels through it at a greater speed, which is 330 meter per second approximately. During the compression, the air cannot lose or cannot gain heat during the rarefaction. That means the process is so fast that the heat loss or gain is not basically fully applied. So the propagation of sound wave through the air, or it has not, basically it is a new procedure which is known as adiabatic procedure. So through air, it has an adiabatic process. Now, what is an adiabatic process? The rapid change in air pressure, volume, and temperature that take place, which is under the action of adiabatic condition. That means sudden changes in the temperature. Now, if we consider this adiabatic process for which we have done the experiment now, we have to consider a new uh, value, which is gamma in this case. Now, we know that pressure and volume are inversely proportional to each other, but we are now considering gamma over here. Now, what does this gamma mean actually? It is basically the ratio between the molar-specific heat at constant pressure divided by molar-specific heat at constant volume. Now, in this case, we are applying this concept in our derivation, which is gamma. Now, where P is the pressure, V is the volume of the gas, and gamma is constant value, which is the ratio between the molar specific heat at constant pressure divided by molar specific heat at constant volume, depending upon the nature of the gas. Now, if the pressure is increased from P to delta P plus delta P, and volume will decrease from V to V minus delta V, then we can say that PV gamma is equal to P plus delta P plus into V minus delta V whole gamma. Now, if we say that this was the equation, P V gamma is equal to P plus delta V into, sorry, this is delta P, not delta V. Let me remove it. It is delta P. Now it will be V minus delta V whole gamma. Now in this case, we have to understand the conceptual value that we are going to take V common over here to basically remove this V gamma from the other side of the equation. So P V gamma is equal to P plus delta P. We are taking V as common, as we know that there is no V over here in this term. So what we do, we multiply by V over here and we divide by V over here as well. So we have V on the top as well as V on the bottom. So we'll take the V on the top as common. So it will be V gamma, and this vector, this component of value, not vector, is going to be 1 minus V is taken from this term as well on the top. So it will be delta V, and the bottom V will remain as it is. So it will be delta V divided by V whole gamma. Now, in this case, we have gotten up to this point. Now, this V and this V gamma basically cancelled out. So what we are left with? We are left with P is equal to P plus delta P into 1 minus delta V divided by V whole gamma. Now, this is the point which we have to gain. Let us remove this one derivation and let's see what happens. So we got to this point, P is equal to P plus delta P into 1 minus delta V divided by V gamma. Now, what we have to do in this case is we have to multiply this P with this one and then P with this delta V divided by V, but we have a power on top. So for that, what we have to do is we have to take a smaller version, a binomial theorem, so that we are only basically understanding those things which are very much necessary for our derivation. So we have to apply the binomial theorem, neglecting the squares of higher powers, or especially delta V and V. So we are applying the binomial theorem. What do we get? This gamma will be now written as P is equal to P plus delta P 1 minus gamma delta V divided by V. So this gamma basically come on to the coefficient part now. Now this is the question which is now we have, that is P is equal to P plus delta P 1 minus gamma delta V divided by V. Now if we multiply these values, so first we multiply this P with these two terms, and then we multiply this delta P with these two terms, and then see what is left behind. Now, P is equal to P, if we multiply the first one, minus gamma P delta V divided by V, and now we are multiplying the delta P part. It will be plus delta P minus gamma delta V divided by V. Now, as we can see, this P and this P will cancel out. It will be 0 is equal to minus gamma P delta V divided by V plus delta P minus gamma delta V divided by V. If we take this negative sign to the other side, it will be gamma P delta V divided by V is equal to delta P minus gamma delta P delta V. Let me clear it out for you. It will be delta V divided by V. So this much part is with us now. But this delta and delta both are very small values, and so that it can be neglected. So what we are going to do is we are going to neglect these values. So this is what we have, that P is equal to P minus delta gamma P divided by, sorry, multiplied by delta V divided by V plus delta P minus gamma into delta P delta V divided by V. So this P and this P cancels out. This negative sign goes to the other side. It will be neglecting this value, all of this value. So what we are left with? We are left with this P, again we are going to cancel. So it is going to the other side, and what we are left with now is gamma P delta V divided by V is equal to delta P. Now, this whole thing, as it is a term, it will go on to the side, it will be positive, and we have left with gamma P delta V divided by V is equal to delta P. So if we take this whole value to the other side, it will be gamma P is equal to delta P divided by delta V divided by V. So we remember that this whole thing was equal to stress, and delta V divided by V was equal to strain. So this is quite similar to the elastic modulus, which was E. So we can say over here that gamma P is equal to E now, and we can put the same value of E in this equation, that V is equal to under root E over rho. So we can say now that V is equal to gamma P divided by rho, and this is the thing which we are going to do in the next steps. So gamma P is equal to P divided by V, delta V divided by V, which is, we know that it is P is stress and delta V divided by V is volumetric strain. So now we know that gamma P is equal to elastic modulus of isothermal process. Putting in the values of the speed of sound of the gas becomes now that V is equal to gamma P, and we know the value of P, which is equal to rho m GH divided by nothing, 1 we can say in this case. Now putting this value of P in this case over here. So here we have, so V is equal to under root gamma into rho mgh divided by rho. By rho m, I mean the density of the medium. It doesn't mean that there's mass included in this equation. So V is equal to under root, putting in the values, we know the value of gamma, which is taken in the case of air. It is taken to be, let me clear that out for you. It is taken to be 1.42. So gamma is calculated out to be experimentally 1.42, putting this value in this equation. So what do we get? We get 1.42 multiplied by 13.6, which is the value of density in the medium, into the gravitational acceleration, which is 980, and the value of h is 76, divided by the density, which is 0.01293 of the air. We get the value of air gamma, which we have already put in, it is equal to 1.42. What do we get? We get the velocity in centimeter, which is 33,310 centimeter per second. When we convert that into meter per second by dividing it by 100, we get 333 meter per second, which is remarkably quite near to the value experimentally which we have found. The values of the speed of sound agrees with the experimental values of which we have found, which was 332 meter per second with the reasonable limits. Therefore, Laplace correction must be correct. That means the short version of this one is that Newton assumed that the whole thing was an isothermal process. The Laplace correction was basically that he assumed it to be adiabatic process, and because of that reason, his answer was near to the experimental values, and that is why we are considering it to be the correct answer and the speed of sound. I hope you enjoyed today's lecture. Inshallah, we'll meet again. Allah Hafiz. Bye bye.